Hi, in this video, we are going to learn about the constraint satisfaction problems. Constraint graph. Here, the constraint graph, the nodes will be the variables and the arcs show the constraints. The main advantage of this constraint graph is this structure will help us to speed up the search. In this constraint graph, now we could see there is a node which is standing alone, which is an independent subproblem because it's not connected to the rest. CSP as a search problem. CSP can be represented as a search problem. Initial state, successor function, goal test and path cast, like any other search algorithm, can be considered. Initial state is an empty assignment. Successor function, it's a non-conflicting value assigned to an unassigned variable. Goal test, which is used for checking whether the current assignment is complete. Then path cast, it is the cast for the path to reach the goal state. Now let us see CSP as a search problem. Here we could see a lot of rooms specified. B2, B3 are the bedrooms. This H represents the hall and this is the dining room and this is the guest room and this is going to be the master bedroom. This is the library. Here we have the study room and here we have the kitchen and the store. Now there are a lot of constraints here. All the bedrooms not in red but only one can. No two adjacent rooms can have the same color. Colors available are red, green, blue and violet. Kitchen is not in green but it's recommended to be blue. Dining it's not in violet. Now those are all the constraints defined. The first step is to represent the search problem using a constraint graph, and this is the constraint graph for this corresponding problem. Once the constraint graph is represented and these are all the constraints. Now here let us look into one point whether there is any need for certain states to be generated or not. Let us start with the hall. This is green in color. Once the hall is green in color, then this B3 cannot be in green. So preferably B3 in blue, red and again it's green. Actually these are all the possible states available in the state space. So options are blue, red, green. But the question is, as hall is green, this B3 can't be in green. As the constraint tells, no two adjacent rooms can have the same color. So this is not required probably. Moreover, this B3 is a bedroom. It's already a constraint is given. It's not in red. Only one can. So why do we prefer the red the very beginning itself? So the question is whether these states are to be generated. So this is a question. Of course, it's not required. Now CSP as a search problem, let us see when this backtracking is required. We start with coloring hall as green. So this is colored in green and then B2 is in blue. So this is going to be in blue. And as you could see, there are a lot of other state spaces. We are just showing only the partial state space. B2 is blue. And then moving on, B3 is violet, okay. And kitchen is blue. Yeah, kitchen is recommended to be blue. Yeah, the constraint is also satisfied. So kitchen is blue. And then comes to the next MB1, master bedroom is going to be a red color here. Now, the next option, in case if we are checking for the dining, what would be the color of the dining? Here it is green, we have blue, we have red, and the only option which is left out is violet, but the constraint tells dining should not be in violet. So this can't be given in violet. That is the reason we can't proceed with that. So we have to backtrack, move on to the previous state. This is backtracking search. And then heuristics. What are heuristics? This heuristics will help in deciding the initial state as well as guiding for the selection of subsequent states. The selection of a variable with minimum number of possible values will help in simplifying the search. This is also termed as minimum remaining values heuristics or most constrained variable heuristic. The main advantage of this is we can detect a failure at an early stage. The variable or the node with maximum constraints is selected over other unassigned variables, and that is called as degree heuristic. So as shown here, instead of the hall, we can choose this variable with the maximum constraints, say dining. The next is forward checking. Let us assume we have three rooms A, B, C and three colors R, G, B. Room A can be painted RGB. Room B can be painted RGB, but it must be different color than room A. Room C, it can be painted RGB, but it must be a different color than room B. Now let's start assigning the colors. For room A, we are assigning red. So room A is now red. Room B can't be red now, and room C can still be any color. Then room B, we are preferring green. Room A is red, room B is green, room C can't be green anymore. Then room C is blue. Now A, B, C rooms are assigned colors R, G, B respectively. Now the constraints are satisfied. Each room has a different color and we have found a valid solution. Forward checking. Forward checking involves looking ahead at the constraints of unassigned variables, and it reduces the domains based on the assignments made so far. The same example let us take. Assignment of room A. We preferred red color for room A, but it reduces the available options for room B and then it updates the domain, which means the colors for room B now includes only green and blue, not red. Likewise, assignment of room B, the choice of green color for room B will reduce the available options for room C and updates domain. So forward checking will help by eliminating green as an option for room C immediately. Now assignment of room C is the last room. There are no more rooms to affect with forward checking. And constraint propagation. This is the process of using the constraints to reduce the domain of possible values. For example, we have a variable x which are taking values from 1 to 10. And we say a constraint must be even. So generally it reduces the domain of x to 2, 4, 6, 8, 10 instead of all the values from 1 to 10. Intelligent backtracking. Now let us assume that we plan for a weekend picnic. We decide on some route based on the fastest routes. In case if we experience some road closures, we have to intelligently backtrack and we will try to explore some alternative routes which are suggested by the app you have. And consider a puzzle solving scenario. When we encounter a conflict or a contradiction while we fill the numbers, this intelligent backtracking generally involves revisiting the previous choices made. It helps in identifying the error and it makes the alternative selections. This iterative process will continue until a valid solution is found. This is going to demonstrate the effectiveness of intelligent backtracking in solving the complex problems by systematically exploring different possibilities. In this video, we have learnt about the constraint satisfaction problem. Thank you.